intermolecular bonds? Well, I guess they're what they say, they're bonds between molecules. Here's some make-believe little molecule, here's another make-believe molecule, and intermolecular bonds would be bonds between those molecules. But how can they be bonds between molecules? At standard grade, you study the bonds inside the molecule. The bonds inside the molecule tend to be covalent bonds. As we discovered when we spoke about electronegativity, it's common for molecules to have charges. So let's take our idea a stage further. Here's our pretend molecule, but it has little charges. It's said to be polar. You might remember what caused the charges was differences in electronegativity. Imagine another molecule with the same little charges. Common sense tells us that opposite charges attract, which means that the negative end of this molecule will be attracted to the positive end of the other molecule. We have an intermolecular bond. Mind you, the charges are very small, and therefore the attraction is very weak. Many intermolecular bonds are so weak they don't really count for very much at all. But let's take things a stage further. Suppose we had bigger charges. How could you end up with bigger charges? That would occur when the difference in electronegativity is large. If there were big differences in electronegativity and the charges were correspondingly big, surely that would mean that the attraction between the molecules would be stronger. And this happens. Now it starts to matter. If the charges are large and the attraction is strong, we can't ignore this intermolecular attraction. This is a hydrogen bond. The question is, when would you get these hydrogen bonds? The answer is, when the charges are large. But when are the charges large? Here's when. When hydrogen is joined to either oxygen, or nitrogen, or fluorine. These three elements occur together in the periodic table. In these three circumstances, the hydrogen ends up with a large positive charge, and the oxygen, or nitrogen, or fluorine, with a large negative charge. The most important one is the hydrogen-oxygen bond, which occurs in water and many other substances. Let's take water as an example. Water molecules are very small compared to most other molecules, but the charges they contain are surprisingly large. As a consequence, there are surprisingly strong attractions between neighbouring water molecules, which means that the positive end of this water molecule will be strongly attracted to the negative end of a neighbouring water molecule, as I say. What does it matter? Does it really matter if there are strong attractions between the water molecules? Yes, it does. And the most important consequence of this is an elevated boiling point, elevated melting point and boiling point. If water had the normal run-of-the-mill weak bonds between the molecules, then the boiling point of water would be minus 100 degrees Celsius, minus 100. That would mean that all the water on the planet Earth would have boiled. There'd be no liquid water, there'd be no life. But water doesn't boil at minus 100, it boils at plus 100. Why is that? Because water has these surprisingly strong intermolecular bonds, hydrogen bonds we call them, which have helped to raise the boiling point of water.